All right, we can now move on to section 2.7, which is going to be integrals, exponential functions, and logarithms. This is actually all stuff you would have learned in Cal 1. I'm just going to combine it with other stuff. So in this one, we are going to need things like the chain rule, integration by substitution, and that kind of stuff to add to what we did in Cal 1. Okay, so with this first thing, it's just defining the natural log in a way that's going to help us. Okay, so the natural log is something that by now I'm sure you have heard of. This is just going to define it in a way that looks nice for us here in Cal 2. Okay, so what they say here is that the natural log of x is equal to the integral from 1 to x of 1 over t dt. Now you may be thinking, how is that helpful? Because it kind of looks a little mean, right? But the reason why is because if I define it like this, I can say that the derivative of the natural log of x is equal to 1 over x because of the fundamental theorem of calculus part 1 you learned in Cal 1. Okay, because remember what that said was that if I take the derivative of something that's like this, I can just plug in x, right? So then that means that the derivative of the natural log is just equal to 1 over x. Now, if I have the natural log of some stuff, right? Like I have like over here, I also need the chain rule. So keep that in mind. So like for example number one asks us to find the derivative of the natural log of 5x cubed minus 2. So example number 1, part A, derivative of the natural log of 5x cubed minus 2. Well, from our rule we just saw, if it's a natural log, it's just 1 divided by that stuff, right? So we start out by just doing 1 over 5x cubed minus 2. But since this isn't just plain x, since it's the natural log of some stuff, because of the chain rule from Cal 1, I need to multiply this by the derivative of that stuff. And the derivative of 5x cubed minus 2, remember by the power rule, I can bring 3 down. 3 times 5 is 15. Times x, decrease my power by a 1, which would make it squared. And the derivative of the negative 2 is just equal to 0. So I don't even need it. So that's it. You could stop right here, or if you really want to, you could write it as 15x squared over 5x cubed minus 2, but it doesn't really matter. They're both right. So this isn't too terribly bad. Again, this is actually stuff from Cal 1. I just want to write it again here in Calculus 2. Example B asks for the derivative of the natural log of 3x squared, the whole quantity squared. Remember, by the chain rule, I'm going to do the outermost part to start with, right? And so here, the outermost part, the very outside thing is the squared, right? It's a bunch of stuff squared. So I'm doing that to start with, okay? So if I have stuff squared, I bring my power to down front, so it should make it 2 natural log of 3x, and then decrease my power by a 1. But since it was 2 minus 1 is just a 1, so I don't even need to put it here, right? Because everything has a power of a 1. So 2 natural log of 3x. But I can't stop here yet because now I've got to find the derivative of the next part. So if I ignore this squared, the next outside part is the natural log. So I do that next. By this rule we had just said, the derivative of the natural log of x is 1 over x. So this time it'd be 1 over 3x, because that is what I have inside. But I still can't stop because I have stuff inside of the natural log. So now, because I've already done this square part, I've already done the natural log part, all I have left is the 3x. The derivative of 3x is just 3. Again, for my classes, I do not care. You could just stop right here. Technically speaking, you could rewrite this because 3's can cancel out, and you could do 2 natural log of 3x over x. But again, for my classes, I don't really care. You could stop right there. Example number C, whatever. The third one is going to be the derivative of the natural log of 2x squared plus x. What did I say? 2x squared plus x. So again, I'm going to do the outermost part first, which is the natural log. The derivative of a natural log is just 1 over that stuff. But then I've got to times it by the derivative of that stuff. The derivative of 2x squared is 4x. The derivative of x is 1. Make sure you put a parentheses around here because that's like saying this times the whole thing, which is what I want. If I left it off, it would be like saying just this guy times 4x. And then all of that plus 1. And that's wrong. It should be times this whole thing. Which again, if you want to, you could write as 4x plus 1 over 2x squared plus x. But it doesn't really matter all that much. Last example, the derivative of the natural log of x cubed squared. Let's do that one. A whole quantity squared. So once again, do the outermost part, which would be the squared. Bring the 2 down, gives me 2 natural log of x cubed. My next part would be the natural log. The derivative of a natural log is 1 over the stuff inside. But then I can't stop because I still got to worry about this stuff. The derivative of x cubed is 3x squared. Once again, you could stop right here, but technically x squared over x cubed, I can reduce that down just to 1 over an x. 3 times 2 is 6, so I have 6 natural log of x cubed over x. But like I said, for my classes, I'm completely fine if you just stop right here. So that is the derivative. So now I can use the same rule to find the antiderivative. So basically it's just the same rule, but then I go backwards. So the antiderivative of 1 over u would be the natural log of the absolute value of a u. Make sure that's there because everything inside of a logarithm has to be positive. And then always put plus c because I could always have a constant there, right? Again, all of this is from Cal 1. So should be a review, but if not, we have that rule here. So let's look at example number 2. Example number 2 wants the integral of x over x squared plus 4 dx. So on first glance, it may not actually look like this, but it really is. Because if I notice, I can use substitution to make it look how this one does, right? Because if I let u be equal to x squared plus 4, the derivative of that is 2x. And I already have x right here, right? So that's really nice. All I need is a 2. I can put a 2 there as long as I put a 1/2 there out front, right? So this becomes 1/2 integral 1 over u du, which we already know the integral of 1 over u du is the natural log of the absolute value of u plus c. But since it started as a dx, this means I want it to turn out with a function of x. So plug back in what we said the u was. We said the u was x squared plus 4. So plug that in. And that's it. Once again, this is right. I'm happy with this, but technically I could rewrite this because x squared plus 4 is always positive. So the absolute value of it isn't going to change it. So if you want to, you could write it like this, but you don't have to. Either way, they are both right. I'm happy with them both. So example number 3 is going to be the same thing. Example number 3 asks for the integral of x squared over x cubed plus 6 dx. I can do the same thing here. I know that because down here, if I let u be equal to x cubed plus 6, the derivative of that would be 3x squared, and I already have x squared. So all I need is a 3. I can put a 3 as long as I put a 1/3 out front. So this becomes 1/3 integral 1 over u du, which is really nice because we know that's just going to be 1/3 natural log absolute value of u plus c. And u we said was x cubed plus 6. So 1/3 natural log absolute value x cubed plus 6 plus c. Now for this one, I cannot do like what I did here because this may not always be positive how that is, right? Because x squared, because it is squared, it will always be positive. And then a positive plus 4 will still be positive, right? So I know that. X cubed may not be positive though, right? So I don't know that, so I have to leave it just like this. So think back to pre-calculus or whatever class you took before Cal 1. We learned some logarithm rules. These logarithm rules are going to help us in this class too, just like they helped us in Cal 1. So just to refresh what those logarithm rules are, the natural log of 1 is always equal to 0. That is because remember that the natural log tells me what the power will be, right? So a power of 0 is always going to give me a 1. So that's why that's true. The natural log of a product, I could split it up and do the natural log of A plus the natural log of B. If I have a quotient, I can subtract them. And then if I have a power, I can bring my power out to the front. So again, these are just rules that are going to help us throughout Cal 2, just like they helped us in Cal 1. So for example, number 4 and 5, it wants us to use these rules here to combine things into one term. So like here, natural log of 9 minus 2, natural log of 3, plus the natural log of 1/3. It wants us to make this into one term using our logarithm rules. So again, we're going to take the natural log of 9 minus 2 natural log of 3 plus the natural log of 1/3 and make it into one term. So first things first, notice there's nothing I can really do over here, right? The natural log of 9, there's nothing I can do there. But with this next term, I have a 2 out front, right? Remember that having a number out front means I could bring it in as the power, right? So this 2 out front, I can make it the power. So this will become natural log of 3 squared. Again, because I can bring my 2 up to be the power. Natural log of 1 over 3, this is a quotient, right? So let's see what happens if I break it up into 2. Like that. Again, because remember we said whenever I have a quotient, right here, I can break it up into 2 by subtracting them. let's see how all of this kind of helped me, right? So first off, natural log of 9, still nothing I can really do there. But 3 squared is 9. So this is natural log of 9. Natural log of 1, we said, is always equal to 0. So that's going to be 0 minus the natural log of 3. Well, why is that nice? Because now I have natural log of 9 minus the natural log of 9. Cancels out. 0 is just that, right? Minus natural log of 3. So this is all equal to negative natural log of 3, which is nice because now instead of having a bunch of terms, I just have one. That's not really hard. Same thing for example number 5. On example number 5, they want us to simplify natural log of 8 minus natural log of 2 minus natural log of 1 over 4. Let's see what I can do there. So first things first, it doesn't really look like I can do very much here, or here, right? But let's see. First of all, 1 over 4 is a quotient. So just like we did on the last one, I can subtract it. Minus natural log of 1 minus, but since it's already being subtracted, I can make it plus natural log of 4. Why is that helpful? Because natural log of 1 is 0. So I can pretend like it's not even there. So now, why does this help us out? Because now I can make this 1 because I'm doing natural log of 8 minus the natural log of 2. So I can bring that in as a quotient. Why is that nice? Because 8 over 2 is equal to 4. So that's natural log of 4 plus the natural log of 4. Since they are both equal to the natural log of 4, that's like saying I have 2 natural logs of 4, which again, a number out front means I can bring it in as the power. So that's the natural log of 4 squared. 4 squared is 16. So like I said, these are just rules that can help us from having a bunch of terms to having only one term, or sometimes it may be actually helpful to start out with the one term and break it into a bunch of smaller terms. These rules help us do just that. So from the natural log, we can get the natural number, which is e. So let's define that. Again, you've probably heard of e a bunch of different times. This is just going to define it so that it's helpful for us here in Cal 2. The natural log of e is equal to 1. So I am defining e to be the number such that the natural log of e is equal to 1. So what that means is if I let the function y be equal to e to the x, this means that the natural log of that is equal to x. Why? Because using our power rule we had just learned, where I can bring the power down to the front, right here, right? I can bring the x down to the front, which would give me x natural log of e, and we just said the natural log of e is 1, so this is going to be x times 1, which is just x. So the natural log of e to the x is just x. Just like we had the logarithm rules, we also have power rules and that kind of stuff. If I have e to the p times e to the q, that's going to be e to the p plus q. This is actually the same rule we had over here. A product means I do plus. Same thing. Product means I do plus. If I am dividing them, I can subtract the powers, and then if I have a power to a power, I can just multiply the powers. We also really like e because the derivative of e is just e, which also means the integral is also just e. But as we always say, remember the plus c. Though the thing that we like to say is that e always just stays e, but then that is because the derivative of e is just e, and then also when I go backwards. So therefore, look at this example here, example number 6a, take the derivative of e to the 3t times e to the t squared. Now, what's really nice about this, I know e stays e, but that's only true if I just have one e raised to some stuff, right? I have two of them here. But it's a product, so based on our rules we had just said, since I have a product, I can add them. So this is going to be e to the power of 3t plus t squared. Now I can use that fact that e just stays e. Haven't taken the derivative yet, so that's going to stay. The derivative of e is just e. So this is going to just stay e to the 3t plus t squared. However, I don't just have e to the t, right? I have e raised to some stuff. So by the chain rule, I've got to multiply that by the derivative of that stuff. The derivative of 3t plus t squared is 3 plus 2t. Again, make sure I put the parentheses here because if I didn't, it would look like I'm only doing this e term times the 3 and not by this 2t, but it also has to be by the 2t. So make sure we have that. Example B, the derivative of e to the 3x squared. Do this the same way. We already said e just stays e, so that's going to start by just being e to the 3x squared, but I've got to now do the derivative of the 3x squared, which is 6x. Again, this is by the chain rule because it's not just e, it's e raised to some stuff, right? Example number 7 wants us to do the integral of 2x e to the negative x squared dx. Now, on first glance, this looks really hard because there's a bunch of stuff happening there, right? But we know e stays e. So if this was just an e, it wouldn't be hard, right? So it would be really nice if this was just e to one term, right? So let's let u, using u substitution, be negative x squared. Let's see if that would be helpful. The derivative of that is negative 2x, which, look at that, I already have 2x. I just need the negative, which I can put there as long as I put one outside too. So this becomes negative integral, negative 2x dx becomes du. So all I have left is e to the u du. And as I know, e just stays e, so this is just negative e to the u plus c, and we said u was negative x squared. That's it. Same thing with example number 8. Example number 8 says let's do the integral of 4 over e to the 3x. Integral of 4 over e to the 3x. First of all, we don't really like things in the denominator, right? So it's always helpful if I can bring it up to the numerator, which I can do by making the power negative. 4 is a constant, so I can bring it out front. So I can bring this up by making it negative. Again, it would be really nice if this was just e raised to just plain x, but it's not. It's raised to the negative 3x. So I want to make it u, which would have to make du equal to negative 3, which I don't have, but I can put there as long as I put one out front in the denominator too. So this becomes negative 4/3 integral e to the u du, which now I can do that. E stays e, so this is negative 4/3 e to the u plus c. We said u is equal to negative 3x, which I could leave just like that, or if I want to, since this is a negative sign there, I can bring it to the denominator, make it negative 4 over 3 e to the 3x plus c. But like I said, I would be fine if you left it just like that too. Either way is fine with me for my classes. All right, so using these rules for the natural log and for e, I can extend it to where they work no matter what the base is. So let's define this. Define y equals a to the x as this. Y is equal to a to the x, which because we said x is equal to that up here, that is the same thing as e to the power of x times the natural log of a. Now, why is that helpful? Because now I can use that to take the derivative of ax, which is just a to the x times the natural log of a. So this is what I really need. The derivative of ax is equal to ax times the natural log of a, which means if I were to go backwards, the integral of ax is equal to 1 over the natural log of a times ax plus c. Same thing, I can do the same thing with the logarithms, no matter what the base is, by multiplying the denominator by the natural log of a. So the derivative of log base a of x is equal to 1 over x times the natural log of a. Once again, all of these were taught in Cal 1. This is just a reminder. So example number 9, let's find all these derivatives. Part A wants us to do the derivative of 4 to the t times 2 to the t squared. Again, it's always really helpful if I can make this into one term instead of two. Notice that 4 is 2 squared, so I could rewrite that as such. 2 squared to the t times 2 to the t squared. Now I have a power to a power, which means I would just do 2 times t. So this is the same thing as the derivative of 2 to the 2t times 2 to the t squared. Since this is a product, I can add the powers and make it 2 to the 2t plus t squared. So now that it's only one term, I can use my rule that I have. The derivative of a base raised to x is going to be the same base raised to the same x times the natural log of a. So in this case, that means it's going to be 2 to the power of 2t plus t squared times the natural log of 2. However, I cannot stop there because this was 2 raised to some stuff, right? So by the chain rule, I have to multiply that by the derivative of that stuff. The derivative of 2t plus t squared is 2 plus 2t. So again, this part is from our new rule. This part is from the chain rule from Cal 1. Let's try another example. Example B wants us to find the derivative of log base 8 of 7x squared plus 4. So remember our new rule for the derivatives of a logarithm is that it's going to be 1 divided by the inside stuff times the natural log of my base. So for this one, that would mean it's 1 over the inside stuff, which is 7x squared plus 4, times the natural log of my base, which is 8. But again, I cannot stop there because it's log of some stuff, which means I need to multiply this by the derivative of that stuff. The derivative of 7x squared plus 4 is 14x. Chain rule, once again. Example number 10 has us doing an integral. Integral of 3 over 2 to the 3x dx. So once again, I like writing these with everything in the numerator. So let's rewrite it like that. Let's bring a 3 out front. 3 integral, that would make it 2 to the negative 3x dx. I know what I do if it's just 2 raised to one thing, but since it's negative 3x, I'm going to let that be u. So du would be negative 3. I already have the 3. I just need the negative, so put that out there. So the 3 goes in with the dx, which would make this negative integral 2 to the u du. We have a rule for that now. It would be 1 over the natural log of the base times the base to the x. So this would make that negative 1 over the natural log of 2 times 2 to the u plus c. And we said u is equal to negative 3x. So once again, this is one of those things where it looks like it should be hard, but honestly, we just used the rule here, right? There wasn't anything we had to overly do. You know what I mean? Last example, example number 11. Integral of x squared 2 to the x cubed dx. So once again, this looks really hard because there's a lot happening here. But notice that I know what to do if it's just 2 raised to like a u, right? So it would be nice if I could let this be my u. But to do that, I would need du to be 3x squared dx, which is fine because I already have the x squared part here. So I need a 3, which is fine as long as I put 1/3 out front. So I end up with 1/3 integral 3x squared dx is the du now, right? So this is just 2 to the u du. So this is going to be 1/3 based on our rule again. Integral of 2, wrong page, would just make this 1 over the natural log of my base. So natural log of 2